Welcome to The Explainer. Today, we're diving into something absolutely fascinating, the hidden assembly line that transforms raw text into lifelike human speech. We hear these synthetic voices pretty much everywhere nowadays, right? But the actual mechanics behind them, well, they are nothing short of an engineering marvel. Let's get into it. So, we interact with synthetic voices every single day. Whether you're asking a digital assistant for the weather, listening to an audiobook on your commute, or just scrolling through social media. But have you ever actually stopped to wonder how an AI translates written words into realistic, breathing audio? I mean, it's definitely not as simple as just matching a letter to a sound. The challenge is actually staggering. To generate high-quality 16-bit audio, the model has to predict from a massive state space of 65,536 possible probability values. And it has to do that for every single time step of the audio. When you realize that just 1 second of speech can contain literally thousands of these time steps, the computational hurdle seems almost impossible.
To make sense of all this overwhelming math, here's our roadmap. First, from robotic to realistic. Second, the neural TTS pipeline. Third, text analysis, the blueprint. Fourth, acoustic models, mapping sound. And finally, vocoders, generating the waveform.
Okay, Section 1. From robotic to realistic.
For a long time, the gold standard was something called concatenative text-to-speech. This old-school approach literally required recording massive databases of audio clips from a voice actor and then awkwardly gluing those pre-recorded fragments together. It was understandable, sure, but highly rigid and, let's be honest, kind of emotionless. Modern neural TTS is a total game changer. It uses deep neural networks to dynamically model the entire mapping process from text to audio end to end. It doesn't glue pieces together at all. It synthesizes the sound totally from scratch, which is what delivers that incredible conversational realism.
Moving on to Section 2, the neural TTS pipeline.
So instead of trying to jump straight from a text document to a complex sound wave in one impossible leap, the standard neural TTS pipeline relies on 3 distinct workstations. It's kind of like a factory. First, text analysis constructs a structural blueprint. Second, acoustic models take that blueprint and map out the sound frequencies. And third, vocoders take those frequencies and perform the final physical audio generation.
Section 3, text analysis, the blueprint. Let's step into that first workstation. The first thing you've got to understand is that the system doesn't just read letters. Letters are way too ambiguous. Instead, it translates characters into phonemes, which are the fundamental units of spoken sound. Think about the word R-E-A-D. Is it pronounced read or read? The AI absolutely must analyze the context of the sentence to assign the correct phoneme before it even thinks about generating a voice.
This stage does a massive amount of heavy lifting. It breaks down document structures so the voice knows exactly where to take a natural breath. It runs text normalization, so if it sees a $sign in the number 32, it doesn't get confused, it knows to say $32. It resolves those tricky homographs, figuring out if you mean a resume you submit for a job or to resume a video. Ultimately, it assigns the precise grammatical stress and expressive rhythm needed before a single sound is synthesized.
All right, Section 4. Acoustic models, mapping sound.
With our rich linguistic blueprint in hand, we arrive at the acoustic model workstation. This acts as the crucial bridge between abstract text and physical audio. The model takes our sequence of phonemes and translates them into an acoustic representation, most commonly a Mel spectrogram. This is essentially a visual map of audio frequencies over time, mathematically optimized to match how the human ear actually perceives sound. You can think of this as complex, highly detailed sheet music generated exclusively for our AI system.
Now, there are 2 main manufacturing speeds for creating that sheet music. Autoregressive models build the sound carefully, frame by frame, step by step. Because every step relies on the previous one, it's super accurate, but it's much slower. On the flip side, non-autoregressive models, like Fast Speech 2, stamp out the whole sequence in parallel simultaneously. This is incredibly fast, but it means the model has to use clever tricks, like variance adapters, to predict exactly how long a word should last before it even generates it.
Some of the most advanced systems actually use a blend of both. Take the cutting-edge VALLE model, for example. It uses a really clever hybrid approach. It generates its foundational audio layer, which contains the core speaker identity, sequentially to ensure accuracy. Then it relies on a non-autoregressive structure to rapidly fill in the remaining 7 layers of acoustic textures all at once. It's just a beautiful balance of high fidelity and high speed.
Section 5. vocoders, generating the waveform.
Our sheet music is finally ready, bringing us to the end of the line, the vocoder workstation. If the acoustic model wrote the sheet music, the vocoder is the physical instrument that plays it. It's the final computational block that translates those intermediate, non-audible visual spectrograms into an actual physical sound wave that can push air through your computer speakers. And make no mistake, the performance of the vocoder completely dictates the ultimate naturalness, smoothness, and crispness of the generated human voice.
Getting that perfect, crisp audio is seriously tough. A state-of-the-art vocoder like HiFiGan pulls this off by using a generative adversarial network. It's basically an adversarial game. You have a generator desperately trying to synthesize realistic audio from the spectrograms. Simultaneously, you have multiple discriminators acting as ruthless critics. The multi-period discriminator slices the audio to check for rhythmic errors, while the multi-scale discriminator checks different audio resolutions. They constantly battle it out, learning and ruthlessly eliminating any robotic artifacts until the audio fidelity is absolutely flawless.
And what is truly amazing here is the efficiency. Advanced algorithms can now utilize neural audio codecs, like encode, to compress and reduce the temporal density of raw, high-bandwidth audio data by a massive factor of 320. Seriously, this is exactly what allows large language models to process complex audio efficiently without getting completely bogged down by the sheer weight of acoustic data.
When you step back and look at the whole factory floor, when you piece together the grammatical and linguistic parsing, the visual acoustic mapping, and that adversarial, high-fidelity vocoding, you are witnessing an absolute interdisciplinary triumph. It takes the very best of traditional linguistics, pairs it with heavy digital signal processing, and supercharges the whole shebang with modern deep learning.
Knowing the incredible math and structure behind this assembly line, it leaves us with one provocative thought to end on. Models trained on thousands of hours of audio can now perform zero-shot generation, instantly cloning a unique voice from just a 3-second sample. As this technology becomes faster, lighter, and completely indistinguishable from reality, how will it permanently reshape what it means to truly hear someone speak? Thanks so much for joining me on this explainer. Keep learning and keep asking questions.